Hi everyone, it's Mr. Kwan here. Today we're going to be talking about limits at infinity. Let's jump into this example. Recall from a previous math class that there is a horizontal asymptote for the function f of x equals 1 over x. Let's examine the graph of the function below. So the function f of x equals 1 over x, it goes through the point 1, 1, and there is a vertical asymptote at the y-axis, and so our graph is going to look something like that. And ooh, that was not good. And their graph also goes to the point -1, -1, and looks something like that. And again, recall that there is a horizontal asymptote here on the x-axis. So pretty much all of the examples we've been looking at examples where you're taking the limit as x approaches some number. So, I have my rational function here. If I evaluated the limit as x approached 4 of our function here, we could just, because it's a rational function, and as long as it doesn't make the denominator 0, we could just plug in the value 4, and so our limit is that value here. But it turns out that you can take limits as x approaches infinity of our function as well. And so it's kind of hard to draw because it's so small, but imagine you have your little person and they have their balloon. If you're taking the limit as x approaches infinity, that just means that the person or the little kid with the balloon is walking to the right forever. And so you're asking yourself, where is the balloon going? And if it helps you to think about that algebraically, what's happening is this value here, the x is just getting larger and larger. So like if you had 1 over a million or 1 over a billion or 1 over a trillion, what's happening is that the overall fraction is getting smaller and smaller and smaller and smaller. So this limit actually does exist, and it's equal to 0 because it's just getting infinitesimally, or I don't think that's a word, not infinitesimally, infinitely smaller and smaller, so it's approaching 0. Same thing if you were calculating the limit as x approaches negative infinity of 1 over x. So you have your little kid, and remember, if it's below the x-axis, maybe think of it as like a magic yo-yo instead of a balloon that goes underground. And they're just walking and walking and walking and walking all the way to the left. And what's happening to the magic yo-yo? Well, the yo-yo is getting closer and closer and closer to 0 as well. So the limit as x approaches negative infinity of this function also happens to be 0. And recall that there is a horizontal asymptote at x equals 0. So these are all important things to note. Let's calculate some more limits at infinity. Before we calculate some more limits, let's discuss properties of certain limits at infinity. So if c is any constant, then the limit as x approaches infinity and the limit as x approaches negative infinity of that constant is just going to equal that constant. And basically all that's saying is that, if you have y, x, and if you had something like y equals 7, so y equals 7, the graph of that is just a horizontal line that intersects the point 0, 7. And so if you had your little kid walking along the x-axis forever in either direction, to the right or to the left, in both of those scenarios, the limit of the function is just going to equal whatever the constant is. And the second property says that if you're taking the limit as x approaches infinity of some constant over x to some power, where that power is a number greater than 0, then that overall limit is going to equal 0. And if you take the limit as x approaches negative infinity of some constant divided by x to the n power, where n is a positive integer, then that's also going to equal 0. And these properties are going to become important as we calculate the limits in the upcoming examples. So example 1 says find each of the following limits if they exist. Now, a really nice way of going about these types of problems is if you are calculating the limit as x approaches infinity of some kind of rational function, what you want to do is you want to divide every term in the numerator and the denominator by x to whatever the highest power is. And we're allowed to do that because basically I'm multiplying 1, in this example, the highest power is 3. So I'm multiplying by 1 over x cubed over 1 over x cubed, which is a fancy way of saying 1. As long as you multiply something by 1, it doesn't change its value. It just changes the way it looks like, its form, basically. Like, if Mr. Kwan throws on a coat, he's still Mr. Kwan, he just looks different. That was corny, I apologize. So basically what I want to do is I want to divide every term by x cubed. So this is going to equal the limit as x approaches infinity of 4x cubed divided by x cubed minus 9x over x cubed all over 8x cubed over x cubed plus 12x squared over x cubed. Now, you might be asking, Mr. Kwan, how does that help us figure out this limit? Well, let's go through and simplify this. So that's going to equal the limit as x goes to infinity of 4 minus 9 over x squared over 8 plus 12 over x. Now, this is where these properties that we were looking at earlier are going to be very helpful to us. Because now what we can do is we can kind of think of each of these limits separately. And so we can take the limit. This is going to be a lot to write out, so let me erase this part here. So you can think of that using the properties from a previous section. You can think about that as the limit as x goes to infinity of 4 minus the limit as x goes to infinity of 9 over x squared all over the limit as x goes to infinity of 8 plus the limit as x goes to infinity of 12 over x. Now remember, if we use property 1 from above, the limit as x goes to infinity for a constant is just whatever that constant is. And then minus, here we can use property 2 to say that this thing here is 0. So 4 minus 0 over, now this thing here is we're taking the limit of a constant again, and that constant is 8. So I can just put 8 like that. And then lastly, here we could use property 2 again from above, and x is going to get very large, so that thing just basically goes to 0. So that becomes 4 over 8, which is equal to 1/2. So that is our overall limit. Okay. Let's move on to part B. And again, similarly, we want to, in this case, the highest power is 4, so we want to divide every term by x to the 4th power. All right, so basically I've just rewritten it so that I've divided every term by x to the 4th power, and then we want to go ahead and simplify that. So that's going to become 6 over x squared minus 9 over x cubed plus 8 over x to the fourth over -1 plus 13 over x squared. Okay, so now this is where we would use property 3 to say that all of these would go to 0, 0, 0, 0, 0. So basically, what we're going to be left with is this is equal to 0 minus 0 plus 0 over -1 plus 0, which if you simplify that, that is equal to 0. So our final limit is equal to 0 here. Part C wants us to calculate the limit as x approaches infinity of the quantity -x cubed plus 1 divided by the quantity 2x plus 8. So again, I'm going to divide every term by x cubed. So if we do that, we get the limit as x goes to infinity of -1 plus 1 over x cubed over 2 over x squared plus 8 over x cubed. So if we simplify that, we get -1 plus 0 over 0 plus 0, which that is an undefined number. So what's going to end up happening is this is a special case where the power of the numerator is the highest power of the numerator, which is 3, is more than the highest power of the denominator, which is 1. And so the output values are going to grow much more rapidly than the denominator is. So another way to think about this is, I'm going to go ahead and erase all of this since that didn't really get us anywhere because we ended up getting -1 over 0, which is an undefined number. So another way of thinking about this is +1 and +8 as you're going to infinity they're so small that they're negligible because they're both just constants. So if you ignored these, it'd kind of be like we were calculating the limit as x goes to infinity of -x cubed over 2x. And so if we simplified that, that is equal to the limit as x goes to infinity of both of those terms have an x, so it'd be -x squared over 2. So hopefully, this is a quadratic function, and if you thought about what the graph of that looked like, -x squared over 2 looks something like this. That is a very rough sketch. So, this goes down forever in this direction. So if you had your little kid with their magic yo-yo, and they're walking forever in this direction, the yo-yo is going off to -infinity. So that was a very long-winded way of saying the limit as x approaches infinity of our original function is equal to -infinity. I also want to indicate very clearly that although I'm saying that these two limits are the same, I'm not saying that this rational function is the same as this rational function. That is not what I'm saying at all. I'm saying that their limits are the same, which is saying something completely different. So just make sure that you have those things differentiated. This last rule says, when we're talking about limits at infinity and horizontal asymptotes, that if the limit as x approaches f of x is equal to b, or the limit as x approaches negative infinity of f of x is equal to b, where b is a constant, then the line y equals b is a horizontal asymptote for the graph of y equals f of x. Otherwise, y equals f of x has no horizontal asymptotes.